At some point, most students make at least one of the mistakes shown below. The square root of x plus y equals the square root of x plus the square root of y. X plus y squared equals x squared plus y squared. Sine x plus y equals sine x plus sine y. Log a plus b equals log a plus log b. 1 over x plus y equals 1 over x plus 1 over y. Unfortunately, each of these statements is false in general. And someone who makes such a mistake is assuming that all functions have the following property, that f of u plus v equals f of u plus f of v for all real u and v. Now, it's clear that there are many functions that don't have this property, but are there any functions that do have it? Well, in fact, we can show algebraically that the function f of x equals 2x has this property. So we first note that for two numbers u and v, f of u equals 2u, f of v equals 2v. And so since f of x equals 2x, then f of u plus v equals 2 times u plus v, which equals 2u plus 2v. 2u equals f of u, 2v equals f of v. So for this function, f of x equals 2x, f of u plus v equals f of u plus f of v. And in fact, any function of the form f of x equals cx has this property. And so these are the functions that look like f of x equals x, or f of x equals 3x, or something like f of x equals pi x. And we can check that algebraically as follows. If f of x equals cx, then f of u plus v equals c times u plus v, which equals cu plus cv. Cu is f of u, and cv is f of v. So again, f of u plus v equals f of u plus f of v. Now, if a function has this property, then it also has another interesting property. So if we take a function with such a property, and we set u equal to v equal to x, then we see that f of u plus v equals f of u plus f of v, so that f of x plus x equals f of x plus f of x, and so we have from that f of 2x equals 2 times f of x. And so for such a function, if we double the input, we double the output. And similarly, f of 3x can be written as f of 2x plus x, which becomes f of 2x plus f of x, and so that becomes 2 times f of x plus f of x, from the fact that f of 2x equals 2 times f of x, and that equals 3 times f of x. And in fact, in general, we can show that f of mx equals m times f of x, where m is some integer. And this last statement tells us that we can pull integer constants out of the function. In fact, with a bit of extra work, we can also show that for such a function, f of m over n times x equals m over n times f of x. And this tells us that we can pull fractions out of the function. So for example, f of 11 over 7 times x equals 11 over 7 times f of x. And at this point you may wonder if we're allowed to pull any real number constant out of the function. So for example, is f of pi x equal to pi times f of x? Well, in fact, in general, we cannot pull any real number out of the function. However, it's possible to show that if f of x is also continuous, which means that there are no breaks, gaps or jumps in its graph, then we can pull any real number out of the function. So the property f of ax equals a times f of x for all real numbers a is true. And so if a continuous function has the property f of u plus v equals f of u plus f of v then in fact it has these two properties. And a function with these two properties is called a linear function. Now we can show that all linear functions map 0 to 0 as follows. If we set u equal to v equal to 0, then f of 0 plus 0 equals f of 0 plus f of 0, which becomes f of 0 equals f of 0 plus f of 0, which finally gives us that f of 0 equals 0. And so we see that any linear function also has this property, that it maps 0 on the x-axis, which is the domain, to 0 on the y-axis, which is the range. Now, it's somewhat difficult, but it can be shown that any continuous linear function that eats real numbers and spits out real numbers must have the form f of x equals cx for some real number c. And so continuous linear functions on the reals are boring functions. Graphically, they are just the straight lines through the origin, i.e. they look like this. So far, we've only been thinking about linear functions that map real numbers to real numbers. Things get a lot more interesting when we think about linear functions that map vectors to vectors. We know that functions can act on vectors, and we are interested in functions that eat 2D vectors and spit out 2D vectors. More formally, we are interested in functions like f, which map from R2 to R2, where R2 is the set of all ordered pairs, and that set represents all the vectors in the plane. Some of these functions are very important in mathematics, physics, and engineering, and these are the so-called linear transformations. A linear transformation T is a function that maps vectors to vectors and which obeys the following rules. T of u plus v equals T of u plus T of v for all vectors u and v in the domain of T. T of au equals a times T of u for all vectors u in the domain of T and for all real numbers a. And of course, these are simply the vector versions of the rules that we saw earlier for linear functions. Linear transformations from R2 to R2 have some nice properties that can be visualized graphically. They map the origin in the domain to the origin in the range, and that means that they don't do translations. They map straight lines in the domain to straight lines in the range, and that means that they don't create curves. They map equidistant parallel lines in the domain to equidistant parallel lines in the range, and that means that they treat the whole plane uniformly. Here we have 4 graphical examples of linear transformations of R2 to R2. First, we have a rotation about the origin. Secondly, we have a reflection in the y-axis. Thirdly, we have a dilation centre the origin. And finally, we have a shear along the x-axis. We shall look at each of these specific linear transformations in more detail in later videos. And here we have 3 examples of mappings that are not linear transformations. Firstly, we have a translation. Secondly, we have a mapping that creates curved lines. And thirdly, we have a mapping that performs a non-uniform dilation. These mappings are not linear transformations because linear transformations don't do translations, don't create curves, and they treat the whole plane uniformly. The first rule for linear transformations says that t of u plus v equals t of u plus t of v for all vectors u and v in the domain of t. At the moment, that's simply an algebraic statement, but it's useful to understand it in a more intuitive way. We can summarize this algebraic statement as saying that if we add in the domain and then transform to the range, then that is equivalent to transforming to the range and then adding in the range. So we add in the domain by adding the vectors u and v, which are both in the domain. We transform to the range by applying the transformation t, and that is equivalent to transforming both vectors u and v to the range and then adding those two vectors in the range. And we can illustrate this statement graphically as follows. So we have two vectors u and v in the domain. We transform those vectors to the range to produce t of u and t of v. We add those two transformed vectors to produce t of u plus t of v in the range. On the other hand, we can add u and v in the domain to produce u plus v. We can transform u plus v to produce t of u plus v, and the statement above says that t of u plus t of v must equal t of u plus v if t is a linear transformation. The second rule of linear transformations says that t of a times u equals a times t of u for all vectors u in the domain of t and for all real numbers a. And we can describe this rule as saying stretch in the domain, then transform to the range is equivalent to transform to the range, then stretch in the range. And we have the following equivalences between words and algebra. And graphically, we can illustrate this statement as follows. We have a vector u in the domain. We multiply by a in the domain. We transform a of u to the range to produce t of a u. On the other hand, we can transform u to the range to produce t of u. Then we can multiply t of u by a to produce a times t of u. And the statement above says that t of au must equal a times t of u if t is a linear transformation. So far, we have only looked at the properties that are common to all linear transformations. However, we need to know how we can algebraically represent a specific linear transformation, like a rotation or a dilation, and given a specific vector in the domain, how we can calculate to which vector in the range it is mapped. So if we have a linear transformation r pi by 2 that rotates vectors anti-clockwise by pi by 2 radians, then we can say that r pi by 2 of the vector 1, 0 equals the vector 0, 1. And graphically, we could represent that transformation as shown in this diagram. So we want to know how can we do an algebraic calculation with the vector 1, 0 that produces the vector 0, 1. And the answer to that question is that we represent a linear transformation with a matrix so that r pi by 2 can be represented by this object, which we call a matrix, and this calculation here represents the abstract transformation shown above, r pi by 2 of 1, 0 equals 0, 1. But the meaning of the matrix and how that calculation works will be left to a later video.